And good evening, AP Physics students. I'm glad you are doing your homework. Speaking of work, that is the topic of today's homework problem. We are going to be checking out number 19 from chapter number 6, which makes use of the work energy theorem. All right. So let's jump right into the problem here. The problem says I have a bow and arrow, okay? And you'll just have to excuse me right away for my drawings of said bow and arrow. But let's say bow and arrow look like so, huh? All right. And I'm told that this string can exert a force of 110 newtons on the arrow, okay? I'm told that the distance from here to here, right, over which the string is exerting a force on the arrow is 0.78 meters, right? 78 centimeters, 0.78 meters. I'm told that the mass of this arrow is 0.088 kilograms, right? Actually, they say it's 88 grams, which is 0.0888, point 0, yeah, that many kilograms. And it wants to know how fast is this arrow going to go? Well, I know it's starting at rest. How fast is it going to go? All right. Now, what we're going to use is we are going to use the work energy theorem to solve this problem. The work energy theorem. What does it say? It says when you do work, you lose energy. No, actually, it says that the total amount of work done on an object is equal to the change in kinetic energy of the object. Total amount of work done on an object is equal to change in kinetic energy. So, if there's only one force being exerted on an object, which in this case there is only one force, right? That would be the strings exerting the force straight horizontally on the arrow. The amount of work done, and we all know that work is FD cosine theta, right? Where theta is the angle between F and D. Now, in this case, theta would be 0 degrees, meaning, right, the force is in the same direction as the displacement, right? So, if the arrow's going this way, the force is going this way, and they're going in the same direction, okay? So, the work done on the arrow is equal to the change in kinetic energy. So that would be final kinetic energy minus initial kinetic energy, right? Okay. Now, notice that both of these equations, both of the sides of the equation are in joules, right? Work is a Newton meter, right? That's a joule. Here we have kilograms, meters squared. I should write this out. This is a kilogram times meters squared per second squared, right? Which is a kilogram times meter per second squared times meters, right? Which is a Newton meter, which is a joule, right? So both of these sides equations are measured in joules. Okay, so the total work done on an object is equal to the change in kinetic energy. If the work done is positive, then the object increases in kinetic energy. Kind of makes sense. If an object's moving to the right and you push on it to the right, it's going to go faster, right? Okay, so work energy theorem. Total amount of work done is equal to change in kinetic energy. Let's see how this would apply to this problem. So to calculate the work done, right, on the arrow, right, I would just start plugging in some numbers here. Cosine 0 degrees is going to end up being just 1 times 1/2 the mass, 0.0088, right? Times v sub f squared minus 0. V sub I is 0, so 0 squared is 0, and that all cancels out. So if we do a little math-a-magic here, we would get 2 times 110, 0.78 times 1 divided by 0.088, right, is equal to v sub f squared, right? Punch that into our calculator, take the square root of each side, and we get v sub f is equal to 44 meters per second. All right. So I applied the work energy theorem to find the final speed of the arrow here. And for your reward, physics students, I have a hilarious cartoon to show you, which I shall do right now. Look at that. Highway Department's reading and comprehension tape. Warning, bridge out. Either speed up or stop. Good stuff. All right, nice work, AP Physics students. See you tomorrow.